Hey everybody, my name is Arthur Rasmussen, and I'm a principal AI engineer here at Weka, and I'm here to give a presentation today on model serving at scale efficiently using the Weka data platform. So let's hop in. So the title of this talk is a blueprint for supercharging LLM inference with paged attention over RDMA. So what that really is essentially a roundabout way of saying we have some technology that is able to improve the efficiency of large language models by several orders of magnitude. And what we're going to do is we're going to dive into what that really means from a point of view of maximizing your investment if you're getting into large language models, especially as a business or as somebody who has a very large established footprint with existing infrastructure, how you can retrofit some technology that we've created into your infrastructure and make the most of that system. So in principle, what we're really talking about is Weka, the file system, as a true extension of the GPU's memory. So that is a claim that obviously requires a little bit of backup, right? So we'll try to go through some of the details. But what we want to really be thinking about during the course of this presentation as, the core point as being the limited size of GPUs, what they can do with their available memory, and starting to augment some of those capabilities with high performance storage, which you can begin to think of as not necessarily external to the GPU, but really an augmentation of the GPU's memory. So here's a bit of an agenda. We're going to go through just a bit of background. We're going to talk about the NIMS platform, so the Nvidia Inference microservices, the TensorRT LLM system, so the inferencing server. We're going to talk about how LLMs work internally. We're going to talk about the pre-filling and decoding stages of large language models, as well as the information that is generated during those processes. So a bit of what the language models actually need to do to understand the text that they're dealing with and give you some text back. We're also going to talk about how multi-tenancy works in large language models. Then we're going to go down and get into some of what the companies that are doing large language models today have done in their systems, the systems that they have deployed in production. Then we're going to talk about some improvements that we've made for those types of systems. And then we're going to go a little bit more deep on how we think about extending GPU memory, some of the considerations that go into extending GPU memory, making performance as good as it possibly can be. And then we're going to talk about the business, Weka, and some of what we're doing, and hopefully make a good case for you for why we're on the leading edge of some of this technology and why you might want to consider coming and helping us to build the future of AI data. So quick thanks to the folks listed here. I apologize if I didn't put your name down. Every one of these people have contributed a great deal to my career, and I'm just very happy to call them friends and colleagues. So a bit of background on me. As I was saying, I'm Arthur Rasmussen. I'm a principal AI engineer here at Weka. Prior to working at Weka, I was an LLM efficiency engineer, and I also worked on the GPU infrastructure team at Cohere. Cohere is a large language model business. They're known for the Command R Plus models. And one of the founders, Aiden Gomez, was one of the principal contributors to the Attention is All You Need white paper, which introduced the concept of the transformer model that is behind all of the stuff that we're seeing these days. And ChatGPT, the explosion of AI that we've seen in recent years. Prior to that, I was the co-founder and COO of a company called Arc Compute, and I've also contributed a great deal to and also founded an open source software community called openiov.org, where I've contributed reverse engineering documentation and open source software to their projects. This is the team that I work with. So these are the folks from the CTO office. There's the CTO, Shimon, on the right side. Every single person in this group, it's an absolute privilege to work with them. They're incredibly talented people, very knowledgeable. Constantly, I'm learning from them. And I'm just very happy to call them all friends and colleagues. So some of the prior challenges that I worked on were particularly relating to how to get models to load into the GPU memory more efficiently, more rapidly. So this is kind of what we were talking about as auto scaling. So this is this idea that when we want to load up a workload, we need to do it in the most efficient period of time possible. We need to minimize the amount of time it takes to start a new workload, to shut down a prior workload, unload anything that it needs to save, then bring up the new piece of software that's going to be running on the system. Some of the challenges that I saw in that technology development, particularly related to the speed of data delivery. So the time it took for us to put the data into the GPU so that it could begin processing the AI model. What I was able to do was essentially to make a series of changes in some software that is used for AI inferencing and make a significant reduction from 10 minutes to start up a model to 13 seconds. That largely had to do with a set of technologies called GPU direct storage and something called TensorRT LLM, which I'll expand on further in this presentation. So TensorRT LLM is an NVIDIA-based inferencing server technology that is widely known for being highly performant. It is the most performant option available for NVIDIA GPUs to perform inferencing. It is one of several very popular servers that exist today. And what it really is known for is in very competitive environments where you have folks that are developing different APIs to perform essentially, token sale or the sale of access to a large language model. What TensorRT brings to the table is really the ability to juice the most quantity of tokens or large language model output out of your GPUs. So you have a constrained resource, you want to get the most performance possible out of it. A lot of people will turn to the TensorRT LLM inferencing server in order to accomplish that. So a bit of background on some of the technologies we're going to be talking about today. So one technology is something called GPU direct storage. GPU direct storage is a technique that can be used to send data into the GPU without the use of intermediate buffering. So some of the technology I've worked on in the past is relating particularly to the internals of the TensorRT LLM inferencing server. One contribution that I made was working on a way where the TensorRT LLM inferencing server could load data directly from the NVMe, so the storage that is GPU accessible, such that the parts of the data that needed to be loaded to the GPU directly to reduce the time to getting that model actually running on the server could be done directly with the GPU, and the parts of the data that come from that model that are required by the CPU can be copied separately. That led to a significant performance improvement in loading the inferencing models. At the core of the Weka technology is the NVMe striping system. It's a mechanism by which we can take blocks of data and we can distribute it amongst many different NVMEs or many different pieces of storage within a large cluster of systems. This is particularly useful for any kind of high performance computing workload where you need the most performance possible. It gives very quick access to any kind of processor that needs to access the data. And really the main point of the technology, or the main benefit of the technology, is that if you have data today and it needs to be utilized by any kind of process, it's very likely not performing optimally. So what Weka technology brings is essentially a way for that data to be accessed more rapidly by any kind of accelerator, any kind of software, and it overall results in a pretty significant performance boost in almost every place that it is adopted. So a little bit on NIM. So NIM is a packaging platform that is utilized for the TensorRT LLM inferencing engines. You can think of it essentially as an app store for AI. One click, you can download AI, you can run various different kinds of AI models. It really simplifies the whole process of getting up and running. So now let's get into a little bit of the internals of these kinds of models. So we'll start out by talking about what LLMs do when they actually are interacting with the data that you give them. One of the first things that they do is they need to ingest information from the prompts that you've given it and convert it into a format that the LLM understands. So what we call that is something called pre-filling. So all of the information that you put into the model can be represented as small little chunks or words or what we call tokens. Those tokens, they need to be put into a format called a vector, which is essentially a representation of the data of the individual words as approximate distances to other words, which provides the LLM with some intrinsic understanding of the meaning. That process, once complete, produces something called a key value, or KV. This is going to be a core concept throughout this presentation, and it really befalls many of the benefits that we can introduce around more efficient management of the key value cache. So the prefill stage is one of two stages that we're going to be talking about. So there's the prefilling component. There's also something called decoding. So if the prefill is the component of the software that takes what you say to it and puts it into a format that's understandable by the large language model, what the decoding phase does is give you back a portion of, or give you back the data that the large language model has processed in a format that's understandable by human beings. Some of the time we see that there's too much decoding. Some of the time we see there's too much prefilling. When these processes in a traditional environment couple together, they're deployed on the same node, we see some degradation in performance because we don't always have the quantity of prefill that we need to be optimal. We don't always have the quantity of decoding that we need to be optimal. So increasingly, businesses are beginning to separate these components into separate nodes that handle their respective functions at the appropriate scale. So what we're going to talk about now is the key value storage. So these are what are called KVs, right? So key values are essentially that memory that the model understands, it utilizes during the inferencing process. That data is what's generated by the model and what's kept when you refer back to it in a later question. So if you say, how hot is it today? And the model says, well, where are you? And then you reply back, I'm in California. What it's doing is it's referring back to those prior messages that have been sent to the model and have been kept in the model as a key value or KV cache. So this is going to be very important throughout this presentation as we're going to really get into the internals of how that data contributes immensely to the overall efficiency of the cluster, and how that data is moved is really a key element in the success or failure of your GPU efficiency. So something we're going to talk about next is LLM prefix caching. So just as we were saying a moment ago, if you have a question, how hot is it today? Where are you? I'm in California or Toronto or wherever you are. I'm in Toronto. Then what we really want to do is we want the language model to keep that context in the system so that when you're going back and asking your follow-up question or you're receiving a follow-up response, it's able to recycle the context from these prior inputs so that it doesn't have to go recalculate all the data for the entire conversation. So this is the traditional design that's used inside of these inferencing systems. This is this concept of paged attention. Paged attention is actually an improvement over the original concept of the attention is all you need, the transformer model. Paged attention introduces this idea of multiple people working on the same resource. So if you have different conversations, you want those resources to be shared amongst the users so that you don't just have one giant box, of hundreds of thousands of dollars of GPUs just allocated to one user. You really want something called multi-tenancy, which is the ability to put multiple users on a given system that can share resources and provide efficient access. So paged attention, when it was initially introduced, was very limited in what it could accomplish. The idea is that it could only really manage the data for the model on one given node, right? So you would have multiple tenants, but those tenants would share a single box, and where the tenancy was managed was on local resources. So you'd have data for the model, you'd have data for the end users, and they would basically be sharing access to the GPU's memory resources and also the CPU's memory resources. So the idea was that one user would have one portion of the memory, one user would have another portion of the memory, and they could essentially coexist on that system without running on top of each other or breaking each other's memory. This, as we'll see in subsequent slides, is actually fairly limited as far as modern inference serving systems. So this is what we're seeing today on modern inferencing systems. There's actually a great deal of inefficiency. We're kind of reintroducing the problem of cache management that originally had been solved for single node systems. What we're finding is that on modern large scale inferencing systems, the key values or the cache data that's managed by the LLM and utilized in multi-turn conversations is starting to be isolated just on individual nodes. You wind up where, with hundreds or thousands or tens of thousands of machines, the likelihood that you as a user will wind up on the same physical box approaches zero. So because of that, we see a lot of this recalculation occurring in a very practical sense. This is often a cost that people are not really thinking about. They realize that, their GPU utilization looks high, but they're not thinking of it in terms of what they could achieve. And hence, this is one of those hidden inefficiencies or these aspects of large language models, which often goes underlooked or goes underappreciated because people are just not thinking about this problem. They're thinking more about just maximizing the way that they perceive their positive metrics. So they perceive the metrics of utilization, not the metrics of cluster throughput. So as we were just saying a moment ago, the inference cluster routing is often just based on very simple metrics: GPU utilization, core occupancy, memory occupancy. The notion that basically when you have a machine, you just look at how much is it processing, if it's processing too much, if there's too much work on that machine, put the user on another machine. And at scale, that often means that the machine that you were paired to is completely different from the one that you may have used in a prior prompt in a long context conversation. So now we're going to be talking about paged attention and introducing some new primitives. So the idea of RDMA for data storage and utilizing direct accesses via the GPU to the memory and retrieving the data for the large language model out of the storage fabric. So really what this is meant to do is solve this problem of the way that the LLM is accessing data, is storing data, and is attempting to recycle its prior work. So what we're introducing today is a technology we're calling paged attention over RDMA. This concept is essentially the idea that the data that the large language model should produce should be pushed into a part of the system which is actually shared amongst the nodes. So the idea is that if you have the large language model produce some work, put it somewhere that every one of the GPUs can access, you can actually restore that data that the language model produced and use it as if it was hot memory. So what we see is anywhere between a 30% improvement, which is already pretty good, to a 4,100% improvements in the speed of the equivalent pre-filling operations when we adopt this technique. So we're going to get into some of those numbers later in this presentation. So let's make our case. So why does storage matter? Why does it not matter? This is kind of a question that is often asked, and it's actually a very important question because it gets to the heart of the issue of how GPUs really work. Under the hood, what makes the difference between a GPU that's utilized, what makes a GPU underutilized, what makes it possible for many jobs of different types to get done in an efficient way where you're not waiting for information to show up on the GPUs. What we're really going to do is dive into the core of that as a problem and precisely what techniques we can apply to improve that type of problem space. So what we see here is a very simple diagram explaining the GPU's memory hierarchy. So as you can see, in the very top level, we have very, very fast memory. That's the closest memory to the core, the place where the processing actually occurs. We see on the HBM, or what we call VRAM, shared memory, it is still quite fast, although it's an order of magnitude slower than the SRAM or the cache memory. And then we see with the CPU memory, so the memory that can swap in and out of the GPU if the GPU is overloaded, that's even slower than the HBM. And this kind of problem typically extends up and down the cache hierarchy. It's a long-term computer science problem. How precisely that memory moves is a question of memory level parallelism, a core concept in computer science. So one of the things we say at Weka is that you can add features, you can't add performance. The main point we're trying to drive here is that at the core of Weka is a very high performance storage file system. So really the main idea is that when you start from high storage performance, you can work up to interesting applications of the technology. You can work up to ways to utilize that high performance storage. But you can't start from poor performance and then try to work backwards into something that is going to really solve the problem of getting data where and when it is needed. The Nsight Systems Compute Profiler allows the machine learning engineers to look at the executing jobs and to analyze them for inefficiencies. This is really focused on the core of the application. So the particular details of how the memory is moved within the GPU and how long it takes to complete various math operations. What they're often looking for, any kind of bottlenecks, inefficient operations, inefficient memory movement. This doesn't take into account all of the perspective though. It doesn't take into account all the possible details. Some of the most important details have to do with queuing data into the GPU, which is outside of the scope of what this utility currently profiles. So for example, if we wanted to go into how long does it take to load the inferencing data? How long does it take to regenerate the KV cache? How long does it take to load up your training data? All of those are out of scope for this utility. They can provide you with a perspective on what happens inside the GPU. They really can't provide you with a perspective of the qualitative work that's being done. Is it work that could otherwise be recycled from a persistent memory storage? Is it work that you could restore from a prior set of jobs that have been executed and have produced a results that can be recycled? All these kinds of ideas of what the GPU is doing are not in scope for this utility. They only really provide you with a perspective of, is the GPU utilized? Yes or no? Not, is the GPU utilized doing the correct thing? So what we're going to do is provide you with an alternative perspective, a perspective on how we can think about the GPU data and the large language model data as not just utilization, but as work that is unique or is not unique. And really, those numbers are the major contributing factor to how much inference can be accomplished within the same frame of time. And therefore, the token economics that are behind that system can be improved or made worse by the performance of all the context surrounding the GPU. So this is typically the way that people think about the stack, right? They start from the idea that there's some storage, a place where they want to load up some program data. They have their application. So in this case, we could say an attention kernel, something that is, running the transformer logic that allows you to do your LLM inferencing. And then they think, about the Nvidia driver, and then the GPUs it runs on. There's actually much more to this story. In reality, what you end up having is you have a storage, right, that holds your checkpoint data or your training data. And then you have a series of components that analyze the code that is a part of that CUDA kernel and make machine level optimizations so that they understand the memory movement. This is really a key part of what makes a difference between an efficient GPU program and an inefficient GPU program. Many details of that programming, the way that the memory movement can be handled, is abstracted from the end user. That's because there's so much complexity in the process of moving memory up and down the GPU memory hierarchy that the end user often can't be bothered to go and optimize at that level. So many of these components that we're looking at here, these are all essentially doing analysis of the code and making very granular improvements to the way that that data is moved within the GPU, so that by the time you as a programmer have written code, you really don't need to worry about all of the details of making sure that that process is optimized. One of the ways that this is possible is because there's a great deal of determinism inside of the GPU in terms of how it processes data, in terms of how the memory movement looks when you're actually looking at, in practice, moving one buffer to another. You kind of know the duration of time it takes to move that data. So that determinism leads to a lot of possibilities from a point of view of the software looking at what needs to be done and making some optimizations around how the data queuing will actually be executed on the hardware. So this is a simplified representation of the way that the process of this analysis occurs, where you have your input as a programmer. You'll have a series of pieces that actually handle the compilation. You'll have a series of representations that the compiler can analyze for inefficiencies and make improvements around. You'll have some components that actually load the code up on the GPU, and then you have your underlying binaries, the things that execute your streaming assembly code, and then you have your resource manager or Nvidia GPU driver. All these components come together when you're running your GPU compute kernel, and all of them are really tuned to get the most out of the memory and the data movement within the GPU architecture. This is a bit of a look at the mechanism that actually performs this alteration of the code. It translates that code that you've given it into, at first something on the left in that green box, which is called parallel thread execution or PTX assembly code. And then at the lower level, it translates it into GPU-specific architecture code or architecturally specific GPU code called streaming assembly or SAS. That particular code is very closely optimized to the metal, and it is precisely aware of the duration of time that it takes for different types of the memory architecture to receive data, how long it should sit there before it begins being copied to the next level, and how long it takes to dispatch various kinds of mathematical operations which transform the data and produce your end results for the GPU compute kernel's operations. So this is what I'm speaking about when I talk about the cycles that it takes for different memory to be accessed and to be used in processing. So you have these different layers of the GPU. This particular set of metrics actually comes from the Ampere microarchitecture. We see that the GPU global memory has a cycle count of 290. We see that the L2 cache has a cycle count of 200. We see the L1 cache has a cycle count of 33. We see that the shared memory for the load and store registers is 23 and 19 respectively. So these numbers are basically just small measurements of the GPU's number of cycles, so just individual turns of the clock on the GPU, how long that really takes for those memory accesses to occur. And what you see in the GPU is that those numbers are completely deterministic. You really know how long it's going to take for that GPU memory to load those registers. There is some slight variation within the GPU depending on how hot those registers are, the proximity of those registers to the places that you'll be dispatching the code to execute on. But by and large, these numbers are essentially accurate to the cycle count within the GPU. While that variation does account for some level of inefficiency within the GPU, there's much more control over the internal memory architecture as compared to external sources of memory, like, for example, the DRAM, which can often be faster or slower depending on the clock speed, or the storage, which often has a great deal of variation in the performance. So CUDA as a programming language is really all about cache synchronization. There are other aspects of it that you can consider, but one of the core aspects of what actually makes it efficient or inefficient has a lot to do with memory management. And there's a great deal of engineering that has gone into it. Actually, I would say an enormous quantity of engineering that has gone into making that process as easy as possible. So from a point of view of a programmer, it really shouldn't be the case that you always have to deal with these kinds of details. Things like PyTorch abstract a great deal of this away from you. When you get into CUDA programming, you get a little bit more of that. When you get into PTX programming, there's more of it. And SAS is like an extreme level of control over the memory movement within the GPU. You start to see that there's actually quite a bit of efficiency left on the table, depending on what exact programming paradigm you're working within. With that understanding, you can work up to the knowledge that the GPU is really just the beginning of the story. You have the memory inside of the device, which gives you all that determinism, which can really help you with managing the complexity of, how precisely long it takes to move different pieces of data around inside of it. You can't really get that same level of determinism from external sources of data. So another key here is this idea of token temperature. So with key values, when you have inputs, you will see that some of those inputs are very frequently reused. So for example, you might say a common phrase like, the cat ran down the road. Maybe that would have a high temperature because you would see many users frequently saying that sort of phrase or utilizing the individual tokens within that phrase. So maybe cat is a common word, and hence the reuse of that would indicate a high temperature on that token. So it would reside commonly in a memory architecture which is the hottest or is the lowest cycle per instruction to access. We'll place those tokens based on where there's availability of memory, and it will determine which tokens to keep in which memory architecture based on the temperature of any given token. So at the highest level, we have VRAM, GPU memory. At the lowest level, we would have S3 object storage. And in the two intermediate sections, we would have the DRAM, which is closer to the GPU, and we'd have Weka, which is just one step up from that. So what we're going to talk about here are the architectural changes that we've made to the inferencing servers. So as you can see here, we have a generic description of just an inferencing server. Inferencing servers, as you know, they handle the attention kernels or the transformer models that actually operate on the GPU. What we have is essentially created a mechanism where the attention kernel can offload its memory. It can write that data out into a shared storage system, the Nvidia GPU Direct Distributed File System, Weka. And that data, once written out into that shared storage pool, becomes accessible to all the other nodes that are participating in this inferencing cluster. What we're going to go through next is what that particular change means in scale serving environments. This is a basic illustration of what inferencing clusters look like in production systems today. We're just going to look at a few of the places where we see inefficiencies in those common inferencing systems and where our additions to the inference ecosystem is able to make improvements around the token economics of inference serving in terms of measured cluster throughput in tokens that the cluster can produce. So here we see a basic environment where we have one user, so one tenant. We have several different machines that are performing inferencing. And we see at the back on the right-hand side, we have a connected file system, which is in common between the nodes that are being used for inferencing. So here we'll get a prompt from the user. There will be a system prompt, and then the question that the user has asked or the instructions for the LLM. That will go through a router, so a system that determines which node to place the inferencing request on. So we'll get a series of blocks that have the user's data. That's just memory that's going to be on the GPU. We have a prefill worker, which is one of the nodes that's going to perform the GPU calculations. That prefill worker will write the data that is produced by the prefill operation into the GPU memory. So now we have a key value block that's tracked by a unique identifier called a hash. That hash is going to be placed in a table that lets us refer to the memory later on based on its hash ID. That hash ID is very simply a lookup that we can perform on input text that we see coming. If we see that the hash ID of the text matches a prior prompt or a prompt for which we have existing cache memory, we can simply recycle the data that is already present in the GPU or present in some form of shared memory so that the recomputation of that input doesn't have to occur. On the decoding operation, we see the inverse. So you'll have the output from the key values go into the decoding worker. It performs the decoding operation, which converts that data into a format that is understood by human beings, so natural language. And then it writes the response back to the user. And then they see that in the left-hand side, where there's a message back from the large language model. So what we've done with our code is to make a change to the inferencing server, which allows us to copy the key value data into a shared memory buffer that can be utilized by all the nodes in that pool. We also see that the memory in the GPU is limited, and so is the memory in the DRAM. So what you will have after a period of time is the memory will become evicted. The low temperature tokens will need to be removed from the system because the memory is not unlimited and because the memory is volatile. So when you shut down a computer, when you have VRAM or DRAM, those are cleared. You have persistent storage, it's kept. So this really acts as a persistent storage layer for the key value data. So if you have a conversation that is several months old, you can come back and restore the existing context of that conversation. So now the user is coming back with another response. So they're asking a question, and what we're finding here is that the router, the inferencing router, is going to make a decision, in this case, that places the user on a different physical node. So a different machine with different storage, with different GPUs, with different memory. So in this case, the LLM has several decisions to make. The first possible decision is that it can regenerate the cache from scratch. So it would have to take all of the inputs, so the tokens that the user sent, the tokens for the responses that the model has sent, and also the system prompt, and it would have to go through the process of converting those back into key values if there's no available location whereby it can restore the cache memory. Option 2 is to restore from Weka. So it can take the data that is in the distributed file system and actually read that data back into GPU memory, even if it's not physically on the same node, due to the fact that the Weka storage system is shared amongst the nodes. The other option is to copy the data directly from an adjacent GPU, which still has active memory containing that KV. Amongst these three options, the cheapest in terms of the number of cycles necessary to complete the memory acquisition will be chosen. What we'd like to provide with Weka is the ability to determine some of those things ahead of time. So we obviously know with a great deal of determinism inside of the GPU what the memory latency looks like. What we really want to do is provide a similar level of deterministic performance in the other layers of that system, particularly the layer that handles the Weka distributed file system. So what we need to do is provide an accurate assessment of how long it takes for the data to be loaded from the Weka platform so that the inferencing server can make the best possible decision amongst its available options for acquiring the cache data. So what we're going to do is gather all the statistics that we can regarding the state of the cluster, the state of the storage, the speed of the underlying storage system, all the various factors that ultimately contribute to the precise quantity of time it will take to acquire that data. And we want to feed that data to the inferencing server so that it can make the appropriate decision. So really what we're talking about here is a high bandwidth, predictable, low latency storage system. This is what brings us to the idea of GPUs and storage starting to cohabitate in a way that allows you to think of storage as more than just a layer of cold data that really has no significant impact on the GPU workloads within the GPU memory. With a high level of performance and with a great deal of understanding about how long different kinds of memory operations take, we can start to give more allowance to the storage fabric to provide us with some deterministic level of memory access performance. And that gets us into, starting to offload more of the core functions of the application into a larger pool of shared storage. So we want to provide the most accurate data we can to the applications that are going to be offloading their cache to the Weka platform. So what we really need to do is take into account all the possible variations that exist in the customer infrastructure that we need to support in our production deployments. There's a great deal of variation in the underlying architectures that we deal with. So we see, some people deploying on InfiniBand. We see some people deploying on Rocky V2, some people on, normal non-RDMA Ethernet. We see variation in the number of NVMEs that are being used to host the Weka file system. We see oversubscription sometimes in the storage fabrics. We see variations in terms of the number of ports allocated to storage, et cetera, et cetera. We see a huge quantity of difference from one cluster to the next. And all of these things we need to be able to handle and to handle in a robust way so that when we see those changes in the infrastructure, that the application can be automatically enlightened about these details without actually having to understand them. It just needs to understand what they mean. All of these factors really weigh heavily on the latency and throughput of that architecture. And obviously all of that really condenses at the end of the day to what the GPU thinks of as the number of cycles per instruction necessary for data accesses. So how do real-time workloads manage this enormous variation in what normally is a cycle per instruction bound set of operations, right? If it's real-time, then how can you really know if you're dealing with these non-deterministic systems? How can you know precisely how long it will take to perform some kind of storage access or read or write? And the basic answer is that you really don't know. And this is often what has led to this notion that storage sort of doesn't matter. It's that because there's so much unpredictability, because there's such a degree of variation, because there is such a lack of clarity on how long that timescale where a performance delay might occur, or on the limitations on throughput or latency, we often see as a result that people really don't think of storage as very important. What we're doing is challenging that notion and starting to push the narrative that storage actually can matter a great deal, and that under the right circumstances and with the right mechanisms to control the variation in different kinds of storage environments, we can begin to introduce storage as a reliable layer for memory accesses. We can assert with some evidence that the storage layer is now a very predictable, high performance, low latency option for storing the data that applications are using in real time. Now, as we've discussed, this is from the DGX reference architecture, we see a great deal of variation in and is often not deployed with the reference architecture, completely implemented. So these are some of the things that we need to determine in order to properly provide an assessment of how fast or slow the storage is in any given environment. So we need to determine the I/O throughput between the nodes that are hosting the NVMe stripes for this distributed system. We need to determine the latency associated with an operation. We need to look at the latency of the underlying NVMe backends. That can vary based on how the storage fabric has been configured, the number of NVMe stripes, the number of replicas, the size of the cluster, the locality of the data that might reside on some NVMe. We need to make a decision between an operation that will regenerate or prefill the cache from the raw text, and then ultimately the alternative, which is to restore from the Weka file system. And all of these factors, they come together to make that decision tree possible. And what we want to do, again, is provide the most accurate assessment of that possible. So what we see here is an optimized architecture for RDMA. We see here we have some high bandwidth memory, so on GPU, and we see that there are a series of network controllers that are differently aligned along the PCIe topology. So what we want to do is we want to utilize the NIC that is physically closest to the GPU in the NUMA topology. So this is all the different possible metrics we'd like to utilize in order to provide the best, predictable performance for storage in a variety of different kinds of applications that will use Weka for caching. We obviously want to take into account how long it takes to retrieve the data. We want to provide, essentially two very basic metrics. Overall, we want to use a variety of different sources of data. We want to use data from the switches themselves, which now can provide some real-time understanding of what's going on in the fabric. We want to see if it's oversubscribed, if there's packet loss, or there's significant latency on packet deliverability. The configuration of the file system that's underneath us, how many NVMEs, how many stripes, how many replicas are within the system. We want to see the type of fabric that's underneath the storage. So we want to see if it's a RoCE configuration, RDMA over converged Ethernet, InfiniBand, normal non-RDMA Ethernet. We want to take all those factors into consideration. We want to look at the number of NICs, the throughput of those NICs, the throughput of the possible storage, the throughput of the storage fabric, the number of ports allocated. All these factors should pool together in one cohesive component that provides us with that real-time understanding of how long the storage data will take to perform IO operations on. So overall, here are some of the results we've been able to achieve so far. So what we see in the blue bar is the quantity of time it would take for us to perform the same equivalent pre-filling operation, so rehydrating our cache, if we were just to take the raw text data and regenerate our key values. And then what we see in the purple bar is just the speed it takes for us to essentially restore the same equivalent data from the shared storage fabric. So we see an improvement function which is fairly robust across the board. We start to see improvements around 50 tokens, where we see a 20% improvements, and then we see the improvement function increase as the token length increases in the conversation. So this is especially useful if you have like RAG queries that are very long context, if you're trying to process very large volumes of data, but it even applies down at those lower token thresholds. Small volumes of text that you input see an improvement function. What we do see though is that in that 41 times improvements is an absolutely monumental sea change in what should be possible in distributed inferencing systems. One way to quantify this very simple thought exercise is to think of a 10,000 GPU cluster where you wanted to add in, let's say, another 3,000 H100s on the value of the H100s themselves. It would be somewhere in the order of $111 million. So that is at the lower end of the improvement threshold. As you get to these larger numbers, so the numbers that are toward the right-hand side of the bar, it's many orders of magnitude better than 20, 30%. So you can imagine the economics that would be required in order to achieve that kind of inferencing at scale without this kind of solution. And with this type of solution, the quantity of processing in dollar value that you can save and also the overall improvement function of your cluster when you're performing large quantities of inferencing. So if you've heard anything in this presentation today that entices you, if you're a customer, you're interested maybe in coming to talk about some of the technology or how you can benefit from this, or you would love to work on the leading edge of AI technology, of storage technology, Weka is a fantastic place for you to consider coming to work. We have an excellent team. We have some of the smartest people in the world, I believe. We have some of the best technology in the entire world. So if you'd love to come and work on some of the hardest problems, some of the best problems to be working on, some of the most exciting problems to be working on, I would very much like to speak with you. So yeah, drop me an email. You can see my email there on screen. We've got offices around the world. We've got an excellent culture, very much focused on, making great technology. We're growing rapidly as a business, and we really want more folks who have excellent expertise in this area to come and join us. So please come consider joining Weka. We really want to have the best minds in the world, and I'd love to talk to you. From my perspective, one of the best things is being able to work with great people. If you want to be a part of something that is fantastic and is on the leading edge of all the most important technology right now. I think if you consider coming to join us, it would be a great journey. You'd probably make some great friends while you're here. You'd make some good memories, and you have the opportunity to work on the leading edge of AI and storage problems. So thank you so much for your time. Hope you enjoy the rest of GTC. And if you bump into me in the hallway, please come say hi. All right, take care.